In last lecture, we have discussed the logical equivalent and we proved the statements, associative law, De Morgan's law, and assumption law. Okay. We have the two statements. We take the two statements in a if and only if statement. It is in a biconditional statement, and the biconditional statement is tautology. Then that two statements are called logical equivalent that we use to prove that these theorems, associative law, um, De Morgan's law, and the assumption law. Now, the next we have predicates. So what is the predicates? Predicates means it is a one type of declarative sentence where the truth value of that sentence it is depending on some variable. Okay. If the and for that variable we have a domain is also given. Okay, like means a predicate is a declarative sentence whose true or false value depends on a one or more variables which are defined on particular domain. Like if we have given a sentence, we have given that p of x equal to is a p of x is a x plus 5 equal to 0. X is belongs to capital N. Okay, so here this is a N, it is a domain of this predicate, this sentence. Okay, now the truthness, the true or false value, it is depending on a value of x. Okay, if the x is a if x is a minus here we cannot take the x equal to minus 5, okay, because x is belongs to capital N. So for all value of x, the px is false. For all value of x, the px is false. Okay, but suppose here in place of domain, the x belongs to capital N. If I am taking x belongs to capital Z, then for x equal to minus 5, the statement is true, and remaining the integers statement is false. Okay, so the statement is true or false, it is depending on a value of x, and here domain is given. If domain is not given, means where the x belongs, that domain is not given, then it is just sentence, it is not statement. But if domain is given and px is given, where the truthness of px is depending on a value of x, then this px is called predicate. Okay, so if we have the in a sentence, if we have only one variable, then it is called predicates with one variable. It is denoted by p of x. If we have the two variables, then it is denoted by p of x comma y. Okay, it is the predicates of two variable. Like if we take p x comma y equal to x square plus y square equal to 4. X square plus y square equal to 4, where domain here we take D, the domain equal to real numbers. Okay, the domain is denoted by capital D. In a predicate, the domain is denoted by capital D. Okay, so here we take D equal to R, the real number. So X and Y are real numbers, and we have the predicates is given by Px comma Y equal to X square plus Y square equal to 4. Okay, the X square plus Y square equal to 4, it is called predicates with two variables. Okay, as on, if we have the three variables, then we write Px comma Y comma Z. Okay, now we take example here. We have given a predicate here. We take the here domain D equal to Z. Okay, for all these examples, the domain we take as a D equal to Z. Okay, the D is a Z. The P of X is given, X is divisible by 7. Okay, X is divisible by 7. So here, if we take the Px, here we take X is equal to, we take X equal to X equal to 7, then 7 is divisible by 7. 7 ones are 7. So 7 is divisible by 7. So P of X, P of 7 is true. If we take X equal to 14, then also P of 14, 14 is divisible by 7. So P of 7, P of 14, these are true. Okay. But if we take the X equal to 5 or X equal to 16, then for X equal to 5, P of 5. So 5 is not divisible by 7. So P of 5, or if we take 16, then 16 is also not divisible by 7. So P of 16 are false. Okay. So here the value of the predicates, the true or false, it is depending on a value of X. Okay. So here we can take this X is divisible by 7. It is known as predicates. Okay, it is denoted by P of X. And here we take the values, this X equal to 14, or then it is true. If we take X equal to 5, then it is false. Now similar way, here we have two more examples. If we have Px is equal to X is a prime number, then if we take the 3, then P of 3 is a true. If we take minus here, if we take 14, then 14 is not prime number, so P of 14 is false. Okay, so P of 3 is true, P of 14 is false. In our third example, we have two variable predicates, that 2x plus y is divisible by y square. If we take the pair 1 and minus 1, then 1 and minus 1, if we put the value x equal to 1 and y equal to minus 1 here, then we have 2 ones are 2 plus minus 1, so it is 1, and here minus 1 square, it is also 1, so 1 is divisible by 1, so therefore we have P of 1 comma minus 1 is true. But if we take x equal to 2 and y equal to 3, then If we put x equal to 2 and y equal to 3, we have 2x plus y is a 4 plus 3, 7, and 3 square is a 9. So 7 is not divisible by 9. Here, 7 is not divisible by 9. So that means P of 2 comma 3 is a false. Okay. Now give me a 2 pair here. For one pair, the statement is true, and second pair, the statement is false. Write 2 pair in a chat box. Write 2 pair in chat box. For the first pair, P of x comma y is a true, and for second pair, P of x comma y is false. Write 2 pair in a chat box, except this 1 comma minus 1 and 2 comma 3. Find the 2 pairs. अभी तक आंसर नहीं आया. 3 comma 4. 3 to the 6 and 4, 10. Okay, 10 is not divisible by 16, right? 3 comma 4 is right. It is false. 5 comma 1. So 10 and plus 1, 11. 11 is divisible by 1, right? 2 comma minus 1. So 4 minus 1. Okay, good. What about 3 comma 2? What about 3 comma 2? P of 3 comma 2 is true or false? P of 3 comma 2. It is true. Okay. So using this way, you can find the true or false for the predicates. Now, mostly the predicates, it is asked in a quantifier. Yes, mostly we use the predicates to define the quantifier. So first we define here quantifier. We have two quantifier. One is a universal quantifier and second one is a existential quantifier. Okay. So in a universal quantifier, the universal quantifier is if we have P of x means one, if we have the predicates defined on a domain D, okay, we have a predicate defined on domain D, then universal quantifier, it is given as P of x for all x belongs to D. P of x for all x belongs to D. Okay, and here D is a domain and it is denoted by this way all x px. Okay, it is read as a all x px. This is a notation of universal quantifier and it is read as a all x px. Okay. So this is a universal quantifier. Now, universal quantifier is true if px is true for every x in a domain. Okay. Universal quantifier is true if Px is true for every x in a domain. Okay. And it is false if Px is false if Px is false for any one value in a domain D. Okay, so it is true if Px is true for all x belongs to n. Like we have write the first statement in a previously that P of x, if I am writing that P of x is greater than 0, and I am taking here domain D equal to capital N. Then for all value of x, the natural numbers are always greater than 0. Okay, so for all values of x, Px is true. So here for this statement, we have all x Px is true. But here, if we take greater than here for this one, I'm taking here in place of x 0, if we take here 1, then what happens? X greater than 1. So, all natural numbers from 2 to infinity, the statement is true. For x 2 to infinity, the statement is true. But for x equal to 1, 1 cannot be a greater than 1. 1 equal to 1, 1 cannot be greater than 1. So that means for P of 1, the statement is false. P of 1 is a false. So we got a 1 point. For that point, the Px is false. So for this statement, the all x Px is false. Okay. So if Px is true for all x belongs to domain D, then then all x Px is true. If Px is false for at least one value of x in a domain D, then all x Px is false. Okay, and this one value of x for which Px is false, that value x is called counter example. It is called counter example of all x Px. It is called counter example of all x Px. Okay, and if we have the domain is a phi, there is no element in a domain, then the all x Px is by default true. Okay, because domain is phi, so there does not exist any counter example. Okay, so by default, the all x Px is true. Okay. Now this is an example. So here, see, in our first we have domain is a R. If we have domain is R, and here statement is given x square is greater than 10. Okay. So when we want to find the value of all x px, the universal quantifier, we always find the counter example. Yes, we check for the counter example. If we got the counter example, then we can write that all x px is false. If we are not, if we doesn't get if we do not get any counter example, then the all x px is true. Okay. So here, which one is a counter example? For which value the x square is not greater than 10? For which value x square is not greater than 10? Yeah. If we take x equal to 2, what about x equal to 2? X square is a 4. It is less than 10. Okay. So P of 2 is a false. So P of 2 is false. So x equal to 2 is a counter example. Okay. So that means all x px is false. Then for the second one, here for second, for x equal to 1, 2 and 3. Okay, these all are counter example. For only for x equal to 4, the statement is true. For 1, 2 and 3, statement is false. So here also, in this one, in a second also, we have all x px is false. Okay. Then for the domain D will be a 11 to 20. So what is a 11 square? The 11 square is 121. Okay. What is a 20 square? 20 square is a 400. So the all x belongs to domain. The x square is a greater than 10 because 11 square is greater than 10. 20 square is greater than 10. So between 11 to 20, the all numbers have a square greater than 10. So for all value of x, px is true. Okay. So here px is true for all x. Therefore, all x px is true. Okay. So to get the value of all x px, we use here, we find the first counter example. If we got the counter example, then we write all x px false. If we didn't get counter example, we write all x px true. Okay. The second quantifier is, okay, so first we have second example here. Here example given that p of x, if it is a given here conditional statement. This is a in a P of X, the conditional statement is given. Okay, so to get the value of true or false, here the two statements are used. The one statement we denote by P, suppose, then P is given here that X is an even number. Yes. And the second statement is given Q that 2x plus 1 is always odd. Okay. So these two statements are given here. Okay. Now to check the value of all xpx, here we have two methods. One is given this way. We take the one by one values. Okay. If we check for x equal to 2, it is a even number. Then we have 2x plus 1. It is a 5. That is a odd number. So the P is true and Q is true. Then the conditional statement is true. So P of X is true. Okay. So if we have the X is a even number, then P of X is true. Then we take the value X equal to 3. That is a odd value. So 3 is not even number. So P, the first statement is false. But 3 into 2 plus 1, that is a 7. 2x plus 1 is a 7. So it is a odd number. So it is true. Okay. So in conditional statement, if first statement is false, then conditional statement is true. So P of X is again true. Okay. So using the example, you can prove that in both condition, if the statement is true. The second way is we write this way. We write the both statement here, P and Q. Now we write the table here. We have P, here Q, and then P implies Q. Okay. Now the domain is given and natural number. In natural numbers, we have two types of the numbers. One is the even numbers and odd numbers. So we divide, if we take the even number, then P is true. Okay, for even number, if we take X equal to even, then P is true. Okay, here we have X is an even. So if we take X equal to even number, then P is true. Here, for even number, even into 2, we get even number. 2 into even number, we get even number. Plus 1, we got odd number. So that means Q is also true. When we have P true and Q true, the conditional statement is true. Then X is equal to, we take odd number. So for odd number, the P is false. Okay, here we put odd number, then odd is not even. Okay, so that means P is false. But if we put odd number here, then also odd into 2 we get even number. Even plus 1 we get odd number. So then also the Q is true. So the conditional statement, if the first statement is false, second statement is true, the conditional statement is true. So that means P of X, the P of X, it is true in both cases, for even number and for odd number. So P of x is true for all x belongs to n. Therefore, all x Px is true. Okay. If we get, if here for any one x we got P of x is false, then we can write that all x Px is false. Okay. So you can use the any one method here. Either use this table method, or you can use the example also. Okay. You can take the one even number and then take one odd number, and in both cases write that P of x is true. So P of x is true for all x belongs to D. Therefore, all x Px is true. Okay. Next we have existential quantifier. So existential quantifier, it is given by here. The statement is given by there exists x belongs to D such that P of x. The existential quantifier, the statement is given by there exists x belongs to D. There exists x belongs to D for that or such that P of x. Now it is a opposite to universal quantifier. Okay, this is notation of existential quantifier. It is read as there exists x Px. This universal quantifier is read as all x Px. Existential quantifier is read as there exists x Px. Okay, this read as there exists x Px. Yeah. Here it has a opposite value as a existential universal quantifier. There exists x Px is true if Px is true for at least one x belongs to D. Okay, and there exists x Px is false if Px is false for every x belongs to D. So remember this thing here. That remember this for all x Px, it is true if P of x is true for all x. Yes. False if P of x is false for at least one x belongs to D. Yes. And there exists x Px. It is a true if Px is true for at least one x belongs to D. And there exists x Px is false if Px is false for every x belongs to D. ये 4 स्टेटमेंट्स अच्छे से याद कर लेना, इसकी जरूरत बार बार पड़ेगी, ठीक है। Now in a universal quantifier, if we have the px is false for any x, then that x is called counter example. Here, if px is true for any x, then that x is called witnesses for there exists x px. Okay, and if domain is 5, then all x px is by default true. If domain is 5, then there exists x px is false. Okay. Now, in this similar example, now find out the value of there exists x px and write in a chat box. Anjali, Ashish, Chintan, Diyesh, Nadesh, Hassan, Sundar, Milan, Nilesh, Sakshi, Prem, Rahul, Swati, Tarun, Yogesh, युवराज, आदित्य, ये लोग तो दिखते ही नहीं है लेक्चर में, क्या है? कॉल करना पड़ेगा। So what is the value? For the first one, we have domain is a real numbers. So if domain is real number, then same way here here you have to find the witnesses. Okay, in all x px we find the counter example. So here we have to find the witnesses. In domain d equal to r, here we take x equal to 4. So if we take x equal to 4, we have x square is a 16 greater than 10. Okay. So we got here p of 4. It is okay. P of 4 is true. So we got the one x for which px is true. So that means there exists x px is true. Okay. What about the second? In second, the same example you can take here. X equal to 4. Okay. So for the second, again, there exists x px is true. For the third, 1 square is a 1, 3 square is 9. So all x belongs to D. The x square is less than 10. So for all x, the px is false. So therefore, there exists x px is false for now here. What about for this one? Write answer in a chat box. Here there exists xpx is true or false. Or write answer in chat box. Here px is a x greater than equal to x square. So for 5 it is false. For 6 it is false. For 9 it is false. For -9 it is false. For 0, the 0 square it is equal to 0. So for 0 it is true. Here for x equal to 0, if we take x equal to 0 here, then what is the p of what is the x square? X square is also 0. So here x is equal to x square. Here equal to sign is also given. So that means p of 0 is true. We got the one witness for which x equal to 0, we have p of 0 is true. So therefore, there exists x vx is true. ओके जितनों ने चैट बॉक्स में लिखा है फॉल्स वो फिर से एक बार अच्छे से आंसर चेक कर लो ठीक है फॉल्स नहीं आएगा ट्रू आएगा if we talk about the all xpx then you are right for all xpx if we take x equal to 5 the statement is false so we got the counter example so therefore all xpx is false here okay but for the x here for this value sorry for existential quantifier means there exists xpx we require the witnesses so we check the all value we got for x equal to 0 we got p of x is a true so x equal to 0 is a witness and therefore there exists xpx is true okay understood yes or no okay. So, okay so now we take the example where you have to find the all values okay First we take here the domain. Here uh, D equal to R. The domain is R. Okay, you have to write the value of all x px, and you have to find the value of there exists x px. यही एग्जांपल हम फिर से रिपीट करेंगे क्योंकि अभी हम सिर्फ ऑल एक्स पी एक्स और देयर एग्जिस्ट एक्स पी एक्स के लिए कर रहे हैं. इसके बाद इसके नेगेशंस भी आएंगे, डी मॉर्गन लॉ भी आएगा, तो उस वक्त ये फिर से रिपीट करना पड़ेगा. पर अभी वो नहीं करवा रहा हूँ क्योंकि पहले अगर इस पे इन दोनों की वैल्यू अच्छे से फाइंड करनी आ गई तो ही वो समझ में आएगा, नहीं तो नहीं आएगा. ठीक है. तो द फर्स्ट वन इज अ first one, p of x equal to is a p of x is a x cube plus 1 equal to 0. Now find out the value of all x px and there exists x px, and write the value in a check box. All x px and there exists x px. So for all x px, first you have to find the counter example for which value the px is false. So here you have lots of counter examples. If you take the x equal to 2, then 2 cube is 8. So 8 plus 1, you got 9. So for x equal to 2, p of x is a false. So all x px is false. Okay. Here for x equal to 2, you have x cube plus 1 equal to 8 plus 1, that is 9. It is not equal to 0. So p of 2 is false. If you got the one value for which px is false, then all x px is false. So here we have false. Now there exists x px. For there exists x px, for there exists x px, here we take here let x equal to -1, then x cube plus 1 equal to -1 cube plus 1. The -1 cube is a -1. The -1 plus 1, so it is equal to 0. So we have p of -1 is true. So we got 1x for which p of -1, it is a true. Okay. So here there exists x px is true. Okay. So this way we can solve this. Okay. The first one is for your understanding. Now Sorry. G equal to R. We have to find the value of all x px and there exists xpx. Yes. The first is done. Now the second, p of x raised to 4 less than x square. X raised to 4 less than x square. Write the answer in a chat box. What we have the value here. Monthly average income, days, days, million, millet, Yaki, grains, Rahul, Swati, Tarun. Only I don't want P of 1 or P of 3 are true or false. I want the value that all x px and there exists xpx. What is the value of all x px and there exists xpx? Okay. You can use the any counter example or any witnesses. Okay. What is the value of all x px and there exists xpx? Both are false. If you take the x equal to 1 or x equal to 2, you got the false value. So it is a counter example. So this is false. But you got the some witnesses also. So this is true, not false. Miller. So find out the witnesses for which value the x raised to 4 is less than x square. Yes, the points between 0 to 1. If you take the 0.5, then 0.5 as a square, see, raised to 4 is a 0.5 raised to 4 is 0.0625 and 0.5 square is a 0.25. So 0.25 is greater than 0.0625. So for 0.5, the statement is true. Okay. So therefore, you got the witness. So there exists x px is true. Okay. बस सिर्फ 3 जन के आंसर आ रहे हैं, ऐसा नहीं होना चाहिए। मुझे सबके आंसर चाहिए। अगर चैट बॉक्स में आंसर नहीं मिले तो फिर मैं 1 बाय 1 सबको प्रेजेंस क्लीन करने के लिए बोलूँगा। The third one is P of x is a minus x whole square equal to x square. What about for this px? ये इतनी देर लग रही है यार। Yes, here for the all real numbers, the minus x whole square, it is equal to x square. Okay, for all real numbers. So therefore, px is true for all x. So px is true for all x. So therefore, all x px is true. Yeah, all x px is true, and here all x are witnesses. So therefore, there exists x px is true. Okay, so both are true. Then fourth, p of x is a 2x greater than x. So here 2x is greater than x. Here for all x px, you have to find the counter example. That is, you have to find the value of x for which px is false. X is false, second is true. Okay. This and Anjali say that This is false and this is true. Any else? Anyone? अभी तक दो के आंसर है, बाकी के just three replied. Rahul, James, and Kuldeep. क्या है और कोई आंसर क्यों नहीं दे रहा है? बाकी सबका हुआ है नहीं हुआ है? Here if you take the negative numbers -1, -2, then the statement is false. For -1, you got the -1 into 2 -2. So -2, it is not greater than -1. Okay, -2 is less than -1. So Px is false for x equal to -1. So that means all x Px is false. And for positive numbers, we take the x equal to uh, your x equal to 1, then we have 2 is greater than 1. So for x equal to 1, P of 1 is a true. So Px is true for x equal to 1. Therefore, it is a witnesses. So there exists x Px is true. Okay. That's one more example. Into x plus 2. divisible by divisible by 3 is divisible by 3. Check. What is the answer here? 8 और 9th स्टैंडर्ड में जब डिवाइजर का जो चैप्टर है ना, वहां पे ये प्रूव करने के लिए आता था. Prove that if we multiply the three consecutive integers, then it is divisible by 3. If you take the x as an integer, then it is always divisible by the x into x plus 1 into x plus 2. It is always divisible by 3. If x belongs to n, okay, for the positive integers. यहाँ पे मैं x इक्वल टू 0 लूँ तो यहाँ पे दिया हुआ है d इक्वल टू r, the real numbers. If I am taking x equal to 0, 0 is divisible by 3. Zero is divisible by 3 or not? For divisibility, we always define the divisibility for non reflexive. Okay, here either we have to take the domain R plus or R negative or Z plus negative or natural number. Okay, because 0, we are not taking 0 in a divisibility relation. Okay. Here for this example, we have to change the domain D equal to R plus, not R. Okay. We have to eliminate the 0 here. If we eliminate the 0 here, the both are true. Now we take the examples from assignment. Yes.